You still cannot, Mel? Okay, now I think you can. Should be able to do now. Yeah.
Yes, okay. Yes, I can share. Okay. Actually, can you hear me okay?
Yeah, that's great.
Okay. Somehow
I heard. I mean, I heard you talk a little bit, couple 2 weeks ago, right? In the but yes. Now I like to hear more. Yeah. Okay. Yeah. So we're very happy today to have Miao Hu. He never gave a talk in this before, so we're very happy to have him give a talk today on the recent excitement on the CDW in the 135. I mean, he has done a lot of work on this. So I want to hear sort of more about the latest development, which is quite different from we had this focus last year, but this is going to be quite different from that, I think. Yeah. Okay. So Miao, it's all yours.
Thank you, Pengcheng, for the warm introduction. I'm Hu Miao from wherein.
We're actually seeing your the present view. Can you switch the yeah?
How about now?
Yeah, that's good.
Okay, great. Yeah. Pengcheng asked me to talk about a little bit charge density wave, which I have been working for a while. But today I probably since Pengcheng already know most of my my results, so I trying to add a little bit more thing about high TC superconductivity and trying to talk a little bit more on other systems. So here going to be a outline of my talk. So I'll start from giving my personal definition for charge density wave, because sometimes I like a definition that's based on physical measurable quantities rather than more theory based definitions. And then I'll give you a very brief review of a charge density wave. This is a very broad field, has a lot of history, so it certainly cannot be a comprehensive review, but trying to tell you what the mechanism might be for the formation of a charge density wave. Then I'm gonna mainly talk about two examples. One is the CW in the cuprate high TC superconductors, and the other one is the CW in Kagome metal / superconductors. And in the end of the talk, I'll give a little bit perspective or outlook of what we are doing and what we will do in the future. All right. So imagine you have, you stand in front of a lake and you throw a stone, then you're gonna say a wave. A consequence of those wave is that it's gonna break the translational symmetry of, let's say, the liquid. And now we can always say, borrowing this idea, we can say, how about we define a charge density wave that is a state of matter that break the translational symmetry of its mother state. So if this is quite broad definition, under this definition, you can say any material, crystalline material can be considered as a charge density wave. This is because if you are a grower, you actually grow a material, then you can grow a material from its gas phase or liquid phase. Once you form a crystalline material, then you break the translational symmetry. But then you're going to say, okay, if you are not a chemist and you are not a grower, you may not be necessarily interested to this process. So let's find a definition that's more specifically related to the electronic state. Now we need to separate. So first of all, we can talk about insulator. We can also talk about metal. For all those mother states, you can have a new state that break the translational symmetry. But here I'm going to say, if the parent state or mother state is an insulator and the emergent phase then break translational symmetry, I wouldn't call it a CDW. Instead, I prefer call it a charge ordering. But if your normal state is indeed a metal and you have a phase that break the translational symmetry, then I generally call it a CDW phase. So this definition we can have are based on measurable quantities. For instance, you can measure the normal states Fermi surface using, let's say, resistivity or RPES, and you can determine if this new state break translational symmetry or not by using X-ray or neutron scattering, et cetera, et cetera. So now we can talk about mechanism. So how do we have a CDW phase? So everything starting from maybe 1930s when Pierce think about half-filled 1D chain, and he claimed for this case you have a divergent stability. Once you have the divergent stability, since it's a half field, you're going to form a charge dimer. The physical picture is that by forming a charge dimer, you're going to open a gap on the Fermi level, enable unclambed scattering. For that, you're going to decrease your electronic energy. If the energy gain over the energy cost for lattice distortion, then you favor a CDW. So later, Kohn, Walter Kohn has studied the consequences of this CDW, and what he discovered is actually for this type of a CDW, you're going to expect a very strong phonon renormalization at the 2kF because of the divergent charge stability, and now this effect known as the Kohn anomaly. So just to give you two examples of quasi-1D system, this one and this one. So you can see using inelastic scattering or neutron scattering, if you study the temperature dependence, you clearly observe this phonon dispersion renormalization that is sharp in Q, which is important because the charge stability presumably very sharp in Q, and that actually supports the Pierce mechanism. Later, people actually find a lot of new CDW materials, which is not 1D. Those materials are generally categorized as transition metal tetragordanite, and then that's motivated people to say, okay, whether this Pierce mechanism gonna still work or not. People studied for a one-band system, the charge stability, as you can see in the panel D, you no longer have a divergent charge stability in 1D and the 3D case. So likely this Pierce mechanism does not work. So that's motivates Maurice Rice and Scott to propose a new mechanism of a charge density wave that's based on a Van Hoff singularity, where they argue if you do have a settle point near the Fermi level, then if you calculate the charge stability, you still can end up in a divergence that's explained, could explain the CDW phase in transition metal tetragordanite. But unfortunately, the V vector predicted by Maurice and his collaborator was kind of wrong and doesn't consistent with experiments. So this mechanism kind of, I think, arguably wrong for transition metal tetragordanite. Later, in 1983, Varma and his collaborator said, maybe we should just think about strong coupling, electron-phonon coupling mechanism. That's probably enough to give you CDW. So unlike those weak coupling nesting picture, that's only consider the lowest Feynman diagram. Now he consider 3-phonon, 4-phonon interactions through coupling with electrons. And based on this method, he actually correctly predict or find the correct CDW wave vector, and he also calculates the phonon response for these materials. And this, he actually predict a Kohn anomaly like phonon softening. But one difference is that for this type of phonon softening, you see it's very broad in Q. This is simply because it's not induced by divergent charge stability that due to nesting, but instead it's very strong momentum dependent electron-phonon coupling. Because of that, this softening would be broad in Q. So that's I would say, a key experimental signature to distinguish the electron-phonon coupling mechanism and the weak coupling mechanism. Using this cis theory, Varma claimed he can reproduce the 2 delta over KBTC in 20 for those transition metal tetragordanite. And more recently, people use inelastic scattering to study the phonon response. And indeed, you can see, unlike those quasi-1D system, you have a very broad phonon softening in the momentum space. So these calculations support Varma's prediction or Varma's theory. So far, we only talk about materials that does not contain very strong electron-electron interaction or magnetism. So for those non-magnetic systems, so the CDW can broadly characterize into two theories. One is weak coupling nesting picture. It could be 1D type, could be saddle point type. But for all those mechanisms, you do expect a Kohn anomaly, meaning you have a phonon boundary normalization that's very sharp in the momentum space. Alternatively, you can have a strong coupling picture where you also have phonon softening, but the softening is very broad in Q space. So these are basically two mechanisms that describe the existing non-weakly coupled CDW materials.
So in both cases, I mean, sorry to ask you, in both cases, you would expect this softening to occur for acoustic phonon. I mean, are there any predictions for optical modes?
For all these theories, only consider the acoustic phonon, but for optical phonon, you could have softening, but it's not included in this theory, as far as I know.
Okay, thank you.
Yeah. Now, the most interesting part, I think, for us would be ask, what happens for correlated system? So for 1D case, it's actually fairly easy. So everything you can go to the Tomonaga-Lachinger model or Luther-Emery model for a 1D case. The starting point is think about a electron, well, the linear band, and you calculate the charge and spin stability. Because the 1D model is the exactly solvable model, people find for a 1D case, you're going to have 2kF divergence in the magnetic stability and 4kF divergence in the charge stability. What I mean is, although for 1D, you shouldn't expect a long-range order, but you do expect these divergences are present in 1D system. How to prove that? If you measure phonons, you should see phonon anomaly at the 2kF and the 4kF. So to give you this is a picture just help you to understand why it's like that. So if you imagine you have a spin density wave and think about how the lattice is going to respond. So the easiest way you can imagine is the lattice response is related to the absolute value of its nearby spin moments. And based on that, you can draw a picture. And for this picture, you will see the spin density wave wavelengths in real space always twice of the CDW wavelengths in real space. Alternatively, you can also say for spin density wave, you're going to have 2kF. For CDW, you can have 4kF. So this picture also necessarily means you're going to have a spin charge locking, meaning the SCW wave vector always half of a CW wave vector. So here is an example that might be fitting into this picture. This is a quasi-1D system. People has been observed the SCW and the CDW, and they also observed this spin charge locking behavior. But this is still in the early stage. This material under pressure also forms superconductivity. We're looking into this material, checking this Kohn anomalies. But so far, just phenomenologically, it may be consistent with the 1D picture. Now, we can go beyond the 1D to look into 3D material and ask whether in a three-dimensional magnetic metal can have a CDW. There actually is at least an example that I'm quite familiar with. This is a pure chromium metal. So this is the Fermi surface, three-dimensional Fermi surface of chromium metal. And they actually have a very good nesting between the zone boundary and the zone center. And if you calculate stability, people predict it should have a SDW in the chromium. Later, Young and Sokolov in 1974, they argue the second harmonic of SDW would necessarily give you a CDW. In 1980s, people use X-ray actually confirmed the CDW in chromium metal until mid-90s. John Hill and his collaborator were systematically studied the CDW and the SDW. Here, there's a remarkable scaling, as you can see here. The triangle is the SDW temperature-dependent SDW order parameter. And for the CDW order parameter, there's a 0.5 scaling. And for this fourth harmonic, there's 0.5 scaling. So this scaling is a very good evidence support that the CDW is actually a higher harmonic of the SDW. So far, all the system, I think we are more or less well understood, and the theory and the experiments are quite receive good agreement. Now we are enter the real beast, which is the cuprate high-density superconductors. If you search the literature, and actually in 1989, 3 years late after the discovery of cuprate high-density superconductor, Rice and Jansanen and Machida already predict a charge ordering or charge density wave in those systems. So what happens is they starting from a Hubbard model or a one-band or two-band Hubbard model, and you use numerical calculation to calculate how the doped holes gonna behave in a 2D antiferromagnetic background. So what they discovered is that when you dope hole into the system, the holes tend to nucleate at the boundary of antiferromagnetic domain walls. And across the domain wall, the antiferromagnetic domain kind of antiphase. So this is easy to understand because if you antiphase, then the electron, if hopping into the domain wall, it wouldn't cause too much energy cost because it still satisfy this AFM interaction, which has very large energy scale. So after these predictions, my former colleague, John Translational at Brookhaven, he discovered this type of CDW in LBCO, and he interprets his discovery just exactly like what Rice and Jansanen predicted in their original paper in 1989. All right, so after that, they actually have a lot of progresses trying to search the CDW in all the cuprates. I think right now, the current stage is the CDW has been observed in essentially all cuprate families. So here, I just want to make a quick summary of what we know about the CDW in cuprate. So first, the CDW is ubiquitous phenomena in all underdoped cuprates. It has been evidenced by numerous experimental techniques and also seems supported by all kinds of numerical calculations, including DMRG or variational method. The second observation is that CDW always forms a dome that kind of peaked around 1/8 doping. The third observation is for all cuprates at a zero field and a zero pressure, the CDW is broadly centered at L equal to half integer, meaning between the two cuprate layers, you have a pi phase shift. So just looking at this, you may guess, okay, maybe all the cuprates should have the same mechanism for a CDW, but it seems not true because people have been studying the doping dependence of the CDW wave vector. Actually, they find two categories. One is the 214 type of cuprate where the CW wave vector increase with doping and saturate above 1/8. But for non-214 cuprates like BISCO 2212 or 2201 or YBCO, the CW wave vector decrease with doping. For the 214, people has been observed the spin charge locking, everything looks consistent with the picture that's drawn and the other theorists proposed, but looking into non-214 cuprates seems a nesting picture works better. So that's posed the question, how do we understand there's on the one hand, we have a lot of commonality. On the other hand, looks like they are different. How do we understand this dilemma? To understand this, we use resonant X-ray scattering. So because significantly improved the energy resolution of this technique, we were able to study the excitation associated with the CDW in the cuprate. And we have been observed a precursor CDW in the RIGs, and we find how those precursor CDW going to couple with the phonon, induce a phonon anomaly, again, in 2 and 4 cuprate. While we're primarily focused on LBCO, Wei-Shen Li on the West Coast focused on BISCO 2212, kind of reached a similar conclusion. So this just explain how RIGs going to work, why RIGs going to benefit, well, why we're going to benefit from the RIGs technique. So basically, unlike the non-resonant process, once you tune your incident photon energy to a certain element edge, then you can access the valency electrons that has this particular orbital character. For instance, for copper L edge, if you excite the electron to the unoccupied state by analyzing the emission electron, then you will know how much the copper 3D electron going to evolve for the formation of a CDW. Here, just to show a spectra, once we tune the energy to the resonance energy, then we can see clearly a CDW peak. If you tune the energy away from the copper L edge, then you no longer see this CDW peak at the soft energy range. All right, so to systematic study, we first look into the RIG spectrum of the LBCO 11.5 dope sample. Here, just to show a spectrum slightly below the CDW transition, you kind of see a dispersive excitation emitting from the CW wave vector. On top of that, you see a strong peak. If you warm up a little bit, and now the elastic peak is gone, but left the inelastic feature almost unchanged. You can look at more carefully by plotting the EDC or MDCs and explore how it evolves as a function of temperature. So in order to understand our experimental data, so we consider a 3 orbital hybrid model, and we can calculate the charge stability. We also specifically consider the phonon, electron-phonon interaction in our correlation metrics. And here is the calculated result. So those are, you can see some sort of a softening because the charge excitation that interacts with the phonon and kind of induce the phonon softening. If I convolute the theoretical calculation with the experimental data, with experimental resolution, then you got the simulated experimental data looks like this. And if you want to compare with our data, it's almost identical. That seems indicating our picture that more or less captured the mean physics for LBCO. We then expand the perform the doping dependence and trying to track how the CDW evolve as a function of doping. Interestingly, we find if you starting from underdoped phase and you warm up, so you find that the CW wave vector actually goes to higher Q. But if you starting from exactly at the one is doping, then it's also it's kind of unchanged. But if you go over doped side, it seems the CW wave vector start move to lower Q as a function of temperature. So here we make a summary. So you find, although at low temperature, well-ordered phase, the CDW wave vector is proportional to a doping level. But once you enter the unordered or short range phase, you immediately see for all those dopings, looks like the CDW always commensurate, move to a commensurate wave vector, suggesting locally the CW is pinned by the lattice.
How do you understand from stripe point of view?
From a stripe point of view,
yeah,
this we cannot tell. We don't know if it's a stripe or not, based on our data. So based on this result, we kind of have sort of a unified picture for all cuprates. So our idea is looking the electronic state from a very high temperature. At a very high temperature, everything is dominated by the Coulomb interaction, and you tend to favor short range, the CDW, maybe magnetic interaction in there. So a good analogy may be the STM image, maybe due to the surface pinning, the STM image somehow mimic to the high temperature phase of the the cuprate system. For all the cuprate in our picture, there should be always the tendency of spin charge ordering, at least the short range. But as you go lower temperature, for some reason, we don't know why, but if the antiphase, antinodal region develop a spin gap, then there's no degree of freedom for you to scatter. Then the nesting picture maybe kicks in. And that's why for non-214 cuprates, you kind of follow the nesting evolution. But for 214, you're going to develop a spin density wave. So once you have that, you're going to have a fairly robust striped picture. That explains why you're going to have a spin charge locking picture. But I want to emphasize for all those mechanisms, they need to be a low temperature phase. But for high temperature, the high energy wise, all the cuprate presumably should be the same. So that's our picture. I think that's all about the cuprate. Maybe I can stop here, take question.
Okay, maybe anybody has any questions for Miao on cuprates? I mean, so I guess, I mean, in John Tranquatta's picture, that at 1/8 is fairly well understood, right? But yeah, when you keep increasing doping, you said that the charge ordering become sort of a commensurate. But I mean, when you increase doping, but then the static stripes sort of disappears, right? Become dynamic. And I thought the incommensurability of the spin fluctuation also sort of saturates. Is there still a 2-to-1 relationship? I mean, your charge order is actually static, right? Not dynamic, right?
We think it should be static, but because our resolution is still on the order of 25 to 30 MeV, we can only say quasi-static. But yeah, we don't know if it's exactly static or not based on our data. We actually studied up to the doping 15.5. We still see a reasonable good spin momentum locking. For LBCL, although I believe there's no static SDW, but the spin gap is fairly small. So I think there's still sufficient, strong interaction between charge and the spin channel. So that's how I understand it.
I see.
Yeah.
But does the charge order in the case of YBCL and Bismuth 2212 agree with magnetic excitation measurement, where people also claim to see this incommensurate, sort of below the resonance and so on and so forth? Do they agree with the same sort of John Tranquatta type of a stripe picture?
No, I think for non-214 there's a huge spin gap. So
I know there's okay. I see. So people don't really know what is the
people don't really know what happens.
Okay,
so that's why I think you really, because the spin is gapped. So at the low energy you don't need a spin to heavily involve. So then the Fermi surface nesting, it's more like a continuum excitation that may be more important, and that's why it's sort of control your CW wavelengths. But the CW fluctuation should be already there, even at high temperature. Actually, Wei-Shen Li from Stanford, they did a RIX measurement at BISCO 2212 at the room temperature, and they find the wave vector actually moved to 0.2, close to 0.25. So that support this kind of a picture. At the high temperature, it doesn't care about the Fermi surface.
Okay.
Yeah.
Are there any other questions for Miao? Okay, maybe you can move to the 135.
Yeah. So then I'm gonna move to the Kagome part, which kind of attracted a lot of interest in the community. So the Kagome structure is now quite new. It's been there for many years. people has been interested in this structure because it generates frustrated spin interaction and can potentially realize quantum spin liquid. More recently, not recently, well, in 2000, sometimes 2000, people are interested in this material electronic structure because it features flat band, Dirac point, and saddle point. And if you combine with topology, you can generate all kinds of novel phase, including fractional quantum Hall, wild semi-metal, or charge ordering, all kinds of phases. Because we're interested in the charge density wave, so I just show what happens near the Van Hoff filling. So the unique part for this Kagome lattice is the interference between these three atoms. So once you consider that and analyze the wave function near the saddle point, people find it's actually orthogonal to each other. So that means the local Coulomb interaction probably not dominant. Instead, the delocalized interaction may be important. So this has been realized in early 2010s, but this kind of physics kind of attracted more interest simply because now people were able to grow material that's realized Kagome lattice, Kagome metal near the Van Hoff filling. So here is the material discovered by Brandon and Steve Wilson. So the structure, they actually has a vanadium Kagome layer, and there are antimony sublattices in there. So DFT calculations show there is indeed multiple Van Hoff singularities near the Fermi level, and then later people actually find the CW in this material. Here, just a summary of the zero field, zero pressure phase diagram of this material. Around 100 Kelvin-ish, it develops CDW. The lattice distortion looks more consistent with Dorff-David or inverse Dorff-David. Then Jiaxing and in Hassan's group at Princeton, they propose for this material, once you enter the CDW, it may corresponding to a loop current. So this scenario is supported by a more recent mu-SR measurement where they see an enhancement of the relaxation rates below the CDW transition. And more recently, there's many curve rotation measurements that show evidence of time reversal symmetry breaking. If you keep lowering temperature, you actually enter a superconducting phase around 3 Kelvin, and the people reported that the superconductivity may intertwine with the CDW order parameter and form a pair density wave. Between these two energy scales, STM study find additional unidirectional phase, at least on the surface, and this observation seems consistent with the resistivity measurement that's showing a C2 rotational symmetry. If you expand your phase diagram, to under pressure, then people find, although the CDW dome CDW phase monotonically decreases via pressure, but there looks like a critical pressure that's for which below the critical pressure, the resistivity, below and above this critical pressure, the resistivity show different response. So indicating there might be two CDW or different kind of a CDW in the phase diagram. But and after this change, the superconductivity also has a crossover from a first dome to a second dome. So this phase diagram is very different from a conventional, BCS type CDW material where the CDW is simply competing with superconductivity. So again, we're using a resonant X-ray scattering, trying to understand the origin of the CDW. The obvious choice would be vanadium LH. That's the excited electron from 2p to 3d. Because if you look at the Fermi surface, all the electrons near the corner are actually coming from the 3d electron. But unfortunately, the photon energy is just too low that we cannot reach any of the CDW wave vector. So alternatively, we say, why don't we go to antimony LH, corresponding to a 2p to 2s to 5p transition, since the p electron indeed crossing the Fermi level, and we do expect certain hybridization between p and d electrons. So we hope using the antimony L1 edge, we should be able to some signature of CDW enhancement. So here is a fluorescence scan. You do see a small resonance at the antimony L1 edge because this p electron is delocalized, so you don't expect a very strong enhancement. Then you may expect, okay, if we go to the CDW wave vector, just like the cuprate, we may see a quite strong enhancement. Actually, we first measured the 2x2x1 CDW wave vector corresponding L equal to integer. Turns out there's no peak. Instead, there's a dip. So the simple explanation is that the 5p electron does not really contribute for this wave vector. But since we are on the absorption edge, so that means the scattering volume for the CDW actually smaller because the absorption. So we do expect a dip for those kind of behavior. And then we move to the 2x2x2 CDW wave vector with L equal to a half integer. Then you can see a very sharp and very strong enhancement at the 2x2x2 wave vector. That demonstrates that the p electron actually involved in the 2x2x2. So just based on this data, it seems to indicate for this particular system, there are actually two CDW order parameters. Similar observation has been observed in other Q, and we're trying to explore as much as possible within the Q range that we can reach. It seems all consistent. So immediate consequence of our observation is that if you have two order parameter and you construct a Landau model, and now you're going to have a cubic term in your Landau free energy, that explains why the system is going to have a first order phase transition. Now, you may wonder whether this 2 CDW going to affect or contribute to the resistivity response, as a function of a pressure. We then performed a high pressure X-ray measurement for the pressure below the critical pressure, PC1 around 0.5, 0.8 gigapascal. The CW evolution is quite similar to the zero pressure CW evolution. But if you apply a pressure slightly higher, the critical pressure, then you see the 2 CW start to separate. And here shows the data, one at the 57 Kelvin, you see 2 CW with quite similar intensity. That once you measure at the 61, then you see only one peak remain, the other is almost gone. So that's actually provide a independent evidence of our proposed conjoined CDW, and that maybe explain why the resistivity have different response below and above PC1, but whether it's gonna induce the superconducting transition temperature need more study in the future. So if you remember the phase diagram I introduced before, STM people actually proposed a what they call nematic or stripe phase, at least on the surface. Initially to us is kind of strange because if you remember the stripe phase, we usually need very strong correlations. But for this material, the correlation is quite weak. It's also, you don't need to consider any strong correlation effect. You can basically reproduce the lattice distortion and the band structure. But then we ask why the system prefer this C6 rotational symmetry breaking. With us, perform the X-ray scattering to test whether this stripe phase observed by STM is a surface effect or bug. To enhance our sensitivity, we actually performed a measurement on the resonance because this structure was observed on the antimony surface. So presumably we should have very strong enhancement on the antimony L1 edge. We're also trying to reduce the fluorescence background by performing our measurement below the resonance. We're trying to improve our resolution to remove all the phonon contributions. For all those measurements, although the bulk measurements, we don't see any evidence of those unidirectional, what they call the 4A0 phase. So we think it's very likely this is just a surface effect. Well, I seem to go surprisingly fast, but so there are some perspectives talk about what we are interested looking to the future. So CDW actually quite common in materials, but now there's an increasing interest to study, to combine CDW and topological excitations. For instance, people were arguing in a wild semi-metal, the wild fermion may induce a CDW, and because the CDW is going to mix a different chirality, so it may give rise axion excitations. Another interesting scenario is if you're starting from a Dirac semi-metal and you apply magnetic field, so you're going to create a Landau level. Once you have that, you kind of have a 1D type of nesting picture, then you're going to generating a 3-dimensional quantum Hall effect. So we are also trying to testing this scenario in a couple of materials. Moreover, you can think about the CDW, if CW can drive a skyrmion, because usually skyrmion emerges when you have DM interaction. But recently, people observe a couple of materials that has tetragonal structure and has the inversion symmetry, but they're still able to observe skyrmions. So, for instance, there's a particular material called European aluminum 4. People using X-ray and neutron scattering measurement find evidence of skyrmions, but they were puzzled because there is no inversion symmetry breaking. Presumably, there's no inversion symmetry breaking, but we know this material has CDW. And here's our X-ray data. We actually show that the CDW couples with the phonon and creates a transverse CDW. Based on simple calculation, we think this CW can actually give you a DM interaction and give you this this kind of skyrmion patterns for this material. And another interesting material was discovered recently or rediscovered recently by Peng Cheng and Ming Yi, where they find in this iron germanium system, they do observe a CDW, and there are also Fermi surface nesting. But the interesting part is the iron germanium and the iron tin actually have quite similar band structure and similar magnetic structure. But this iron germanium has a CDW transition. And more intriguingly is if you look at the DFT calculation of a phonon spectrum, the phonon is actually very robust. So that seems indicating for this system, the strong correlation has to be taken into account in order to properly understand the CDW. We are also start working on this material. Hopefully, I can share more insight in near future. So before I finish, I just want to advertise. So now DOE support, graduate students use the resource of National Lab, and they actually give a pretty good monthly stipend. You can cover your living cost. We also provide a little bit of funding for your research. So if you are interested in those opportunity, please contact me. We can discuss. And thank you for your attention.
Okay. Yes. Thank you. Well, yeah, it's a very, very nice talk. I mean, also some really new results. Yeah. Yeah. Okay. So any questions for him? Oh, Jeff, I can see you finally.
Yeah, I finally got the connection correct. So I have one question on europium aluminum 4. I remember, I mean, the charge density wave is along the phi axis, and the skyrmions are in the AB plane.
Yes.
That gives you enough antisymmetric exchange to form the skyrmions? These are very small. These are very small skyrmions.
These are very small.
Yeah, they're almost
actually, Miao, is this are these small angle neutron scattering data or just sort of made up patterns? I haven't read this paper.
These are small angle scattering.
Yes.
Okay.
You just have to thin the crystal down a lot. We also did the 122 material, but we did not see the skyrmions.
Yeah, so I think it's a very good question. So what we find, we actually perform the elastic scattering measurement, trying to probe the transverse mode and the longitudinal mode. We see nothing in the longitudinal mode, but very strong response in the transverse mode. So what I mean is the lattice distortion is actually is perpendicular to the CW propagation wave vector. And more exciting thing is we were able to develop, well, my colleague were able to develop a TEM, directly visualize how the atom is going to move. So we find there, at least the mirror symmetry is broken. And if you only look into the European plane, it's the broken symmetry actually gave you DM interaction. And we calculate DM interaction, which favor kind of a spiral spin orientation in the plane. So at least the direction makes sense. But whether the magnitude can give rise to the skyrmion, we don't know. But at least it looks like can qualitatively consistent with the neutron scattering measurement.
So Ming, you have a question?
Oh, yes. Hi, Hu, good to see you. I just wanted to hear, given everything that you know about the Kagome system, what is your take on the role of Fermi surface nesting versus electron-phonon coupling for the charge density wave?
It's a tough question. Well, to be honest, I personally, I in general don't believe a nesting can drive CW in 2D and 3D systems, simply because the divergence isn't strong enough. For instance, even for the AVS, there's a lot of evidence supporting the nesting picture. But let's say, imagine we have a divergent charge stability, right? So if we start in cooling from high temperature to low temperature, as long as we have tiny bit of electron-phonon coupling, we should already see some kind of a phonon softening slightly above the onset temperature. But we see, I think both me and Peng Chen see nothing. So what that means is at least the charge stability does not diverge slightly above the CW transition temperature. Whether it contributes for the formation, this I don't know, but I think Fermi surface nesting alone may not work.
Okay.
Okay. Any other question for him? Okay, so there's on the chat. So Miao, very good talk. Thanks. I have a question on C6 symmetry breaking of 135. If it is a surface effect, how do you understand NMR peak splitting in the Nature paper?
I think the question is asking.
You asked the wrong guy, right? He's not an NMR guy.
Yeah. Well,
I mean, although you know, yeah.
I think well, our picture we actually had. Let me see if I can have. I think I have it. So I actually had very small paper trying to simulate to understand. Well, initially when Jiaxin report this different Bragg peak intensity, my immediate reaction is just a structure effect. So in order to understand that, I did some simple simulation and trying to understand the pattern. So it turns out if you have because there's two layers, the 2x2x2. If you have a pi phase shift between the two layers, but still keep the same inverse of star of David, then you can actually generate the STM observe the intensity. So you see, so this is a simulation. I just assume the nearby adjacent layers have a pi phase shift. Then you can observe two peaks weak, on the other four is strong. but I cannot explain why it should respond on the magnetic field. But nonetheless, I think once you form the 2x2x2 CW, you automatically break the C6 rotational symmetry. But there's no strong correlation stuff or electronic part. It's simply structure effect to me.
Mm-hmm. So to what order of magnitude can you claim that the STM measurement seeing the implant C4 rotational symmetry, C2 rotational symmetry breaking are purely surface effect? To sort of what accuracy you can claim that?
That's a very good question. So we had a hard time to argue with the referee because referee say, okay, you guys probably not sensitive enough. So we did a calibration based on our intensity, and we find if the 4A0 phase is real or Bach, so its magnitude is 10 to the 3 order magnitude weaker than the 2x2x2.
I see. So you have a calibration. Okay.
Yes.
So that's pretty convincing then, right? I mean, it's really the surface effect that how do you understand the Haihu's data where he claimed the transport is also
actually twofold? You Haihu's data, as I just explained, once you form a 2x2x2, you already break this C6 because the sliding of the layers. So Haihu's data, you see the onset is actually from CDW. So it's just the electron-phonon coupling. So the lattice already has a C2 symmetry, but the electron-phonon coupling usually have very strong temperature dependence because the Fermi factor in the electron-phonon scattering and also the formation of a CDW gonna reduce your density of state. For all these factors, if you consider the electron-phonon coupling will progressively enhance once you go lower temperature. So that's going to enhance your C2 effect in the electronic part. So we think that's probably why you can see that.
Okay. Do you have any understanding on the Liang Wu's result? Liang Wu is going to give a talk next month in October, early October, about his result on the C4 rotational symmetry breaking. But
yes, I think I don't know. The one thing I'm not quite confident because I'm not fully understand the cross section of this curve rotation. It looks like conventionally you consider a coupling, a dipole effect, but that's maybe, I don't know, the moment seems quite large in order to reproduce the experimental result. But more recently, I think a Japanese group reported this kind of a curve effect show fairly strong magnetic field dependence. So to me, it's even more convincing that there are some magnetic components in there. So that's I think all I can comment.
Okay, thank you. Any other question for him? Okay, well, if not, yeah, great. Yeah, thanks a lot. Yeah.
Yeah,
for giving
terrific talk.
Yeah, stimulating talk. Yeah, this is really very interesting field. Yeah.
Thanks.